So today's lesson is going to be on quanta of light. This is where we look at light being more acting like a particle than a wave, but it still ties into the wave model of light as well. So we're going to look at the singular unit or quanta of light today called the photon. We're going to connect the concepts of energy, frequency, speed, and wavelength of light all together in one today. We'll do several examples that we're going to work through together and then look at some practice. So first of all, Planck's quantum hypothesis. I want to just start by saying white light produces a continuous spectrum. We've seen this before, of course. White light can split into all different colors of the rainbow, but how does frequency of monochromatic light, so light of one certain color, affect the light's intensity? In other words, how is it that one color, let's say red, is more or less intense than green? Is there a correlation? Is there no correlation? Well, let's see. An ideal incandescent object is called a black body. A black body absorbs all EMR that falls upon it. None is reflected. So in other words, it's a perfect object that all of the electromagnetic radiation that strikes it gets absorbed by that object itself. The absorbed energy from the EMR re-radiates as thermal energy, so as heat. Therefore, all of the energy emitted by a black body is directly related to its temperature. We won't need to know too much about this, but it's just important to understand a black body is an ideal object that will absorb all EMR and then re-emit it as thermal energy. This is a little chart that kind of shows it. I'm not going to explain it because we don't need to know it. Same with this slide. I'm not going to go through it. Basically just explains that different things burn at different colors for reasons related to specific frequencies and their black body radiation curve. But we don't need to know that. So moving on. Planck. In 1900, after years of work, Max Planck derived an equation that described black body radiation. Planck's theory, however, required an assumption that oscillating atoms and molecules are quantized. That is, they could only emit energy in specific step values called the quantum energy. In other words, it's not a continuous range, right? In other words, the amount of energies that things could release are in little steps, right? There's not like in-between values. Many scientists had trouble accepting the idea that energy was not continuous in this regard, with quite good reason. You'd think, you'd be able to slowly, gradually increase your energy, but really it has to happen in little steps. Now, Einstein extended Planck's hypothesis, used to describe molecular energy to explain the nature of light. He reasoned that light must have energies in discrete values, so not continuous. Discrete means little steps, and must also be quantized. A quantum of light, so a singular unit of light, is called a photon. So every photon that you add to it is a new quantum, right? Just for another analogy with this, we know with electric charges are also quantized. One electric charge is an electron, right? So as you gain additional electrons, you gain additional electric charges, right? So that's also not continuous. It's the same kind of idea with energy in light. Light only follows certain photon levels. One photon is one quantum or one unit of light. So Planck's equations, he had two equations. Both of these are on your formula sheet, but I'll tell you a little thing about the first one in a second. E equals NHF is one formula you can have. That would be if you had frequency. Or E equals HC over lambda. Lambda, of course, is your wavelength. C is the speed of light. So E is the energy in joules or in electron volts. Remember, it's been a long time since we've talked about electron volts, but electron volts are just another way of representing energy. They're not quite as common as joules, but we use them every now and then. N in this equation would represent the number of photons that you have. H is Planck's constant. This is on your formula sheet in the data section. There's two different values for it. 6.63 times 10 to the negative 34. That's like the smallest number we've ever seen in this course. And the units are joules times seconds. That would be used if you wanted to find your energy in joules. But if you didn't want it in joules, you wanted it in electron volts, you could use 4.14 times 10 to the negative 15 electron volts times seconds. So that would, of course, spit out electron volts. F is your frequency in hertz, C is the speed of light, and lambda is your wavelength, as it usually would be. Now, as I'm sure you've already read it as I was rambling there, yes, these are on your formula sheets, but the N doesn't actually show up on your formula sheet. But really, it's not that big of a surprise. Keep in mind, E is the energy that's being produced, right? And if you have many photons, many quantum of light, you would just multiply by however many photons you had. So if you had one photon, you wouldn't have to worry about the N. So really on your formula sheet where it says E equals HF, that's talking about the energy of one photon. But if you had many photons, you just have to multiply by the number of photons. I don't know why I didn't put it in this equation as well, but really it still applies on this one as well, right? So E equals nhc over lambda. That would be the same thing. This is as it appears on the formula sheet though, so whatever. Basically, you just need to know if you have more than one photon, just multiply it by however many photons that you have. So in these formulas, the energy calculated is the value of the quantum, so one photon, the difference between each level of energy for EMR, right? So as you add more photons, you gain more energy. Because Planck's equations show a direct relationship between the energy of a photon and the frequency of the radiation, the electromagnetic spectrum is also a spectrum of energies. Gamma rays are the highest energetic radiation, and again, that's because gamma rays have the highest frequency, and radio waves are the lowest energetic, right? Because they have the lowest frequency. Remember, frequency and wavelength are inversely proportional to each other. Radio waves have a very long wavelength, but a very long wavelength means a very small frequency, and vice versa, right? So gamma rays, in other words, those are the highest energy. Radio waves are the lowest energy. And that really shouldn't be a surprise because we've talked before about how gamma rays and X-rays are very dangerous. They can cause a lot of damage to living things. That is related to the fact that they have so much energy contained in them. They're way higher energy waves. They're a lot more dangerous. Another conversation that comes from that is microwaves, which are second lowest in energy to radio waves. This comes as a surprise to a lot of people because you think if you use your microwave oven, it seems to add a lot of energy to the food that's in the oven, right? Well, this is related to a couple different things. One, your microwave oven is producing a ton of microwaves, right? So you have a huge amount of photons that are being emitted inside that microwave oven. So that, of course, is going to really ramp up the energy. But another reason that microwaves are so effective at cooking food is actually because microwaves, again, oscillate at a certain frequency, and that frequency resonates with water very well, right? So in other words, that frequency of a microwave, when it strikes water molecules, the water molecules start vibrating with them. And vibrating particles is, of course, how we measure heat. Heat is just how fast things are vibrating, if you really wanted to simplify it down. So, of course, if microwaves are making water molecules vibrate really fast, therefore, it's going to heat up the food really fast, right? That's the whole idea. That's why certain foods will heat better in a microwave than other foods, right? So really dry foods don't usually work too well in a microwave, but really, water-containing foods would, right? Anyway, that's a total aside, moving on. So here's an example. Determine the range of energies in electron volts for visible light. Now, to determine the range of energies, we have to look at the lowest energy and the highest energy. And the only way we can do this is using that chart that I've put at the very front of the note package that shows the wavelengths of different parts of the visible light spectrum. The lowest wavelength is violet light, which the lowest range of it that humans can see is about 380 nanometers. So let's start with this one. If we're going to go through this question, we can say that we'll start with the minimum wavelength. Remember that E, energy, is hc over lambda. Of course, lambda is wavelength, so we have no choice but to use this formula. We can't use the other one where it's E equals hf. We have to use this one because, again, we know lambda. We can just throw our numbers in here. Again, we're looking for electron volts, so we might as well just say E equals, we have to use h that's in electron volts. That was 4.14 times 10 to the negative 15. Oops, not negative 5, my mistake. 10 to the negative 15. Times by c, which is the speed of light, 3.00 times 10 to the 8, all divided by your lambda, which again, if we're going to start with violet light, we'll look at 380 nanometers, that's times 10 to the negative 9 meters. Throw this in a calculator, and you're going to find that E equals, in electron volts, 3.27 electron volts. So I'll put a box around that. That's going to be one of my answers. Now, if we use the other end of the visible light spectrum, the highest wavelength of light that we can see is really red light, right? So in other words, 750 nanometers, as that chart shows. So we'll do this one more time. We'll say this time E equals h, once again, 4.14 times 10 to the negative 15, times by c, which is 3.00 times 10 to the 8, divided by your wavelength. This time we'll use that maximum wavelength of 750 nanometers, so 750 times 10 to the negative 9. Throwing this in your calculator, you know what, I'll just write it proper. We'll say E equals 1.66 electron volts. So notice with your maximum wavelength, you got your minimum energy, and with your minimum wavelength, you got your maximum energy. These two numbers in tandem with one another, that forms your range of energies. So in other words, for visible light, light that we can see, the range of energies goes between 1.66 electron volts and 3.27 electron volts. There you go. So anyway, moving on. Next one, a helium laser produces light with a frequency of 4.74 times 10 to the 14. What's the energy of the photons produced by this laser, right? All right, so by the energy of the photons, I can reasonably assume it's talking about each individual photon, so not all of the photons, just we're gonna look at one photon at a time. We have a frequency. This means we get to use that even simpler formula where it's E equals HF. Since we are looking for energy, we have a frequency, H is a constant, we're good to go. Now, it doesn't say what units it wants the energy in. Generally speaking, if it doesn't say the units, I think joules is probably a better one to go with, because joules are just a more familiar way of measuring energy. So let's use the joules one instead. So E equals, we'll use the joules H, which is 6.63 times 10 to the negative 34. And we'll times that by our frequency, which is 4.74 times 10 to the 14. Throw that right in your calculator, and you're going to get 3.14 times 10 to the negative 19 joules. That would be your energy as your answer. If you wanted to use electron volts, just an aside, you could have used that 4.14 times 10 to the negative 15 instead, or you could convert this number directly. But either way you do it, another answer would be E equals 1.96 electron volts. Not a huge deal, but still good to know. Next one, X-ray photons are produced when electrons are rapidly accelerated. That's kind of how all photons are produced, when electrons are accelerated, or any charged particle really. If a charged particle is accelerated, that's going to produce photons. Later on in this course, we'll talk about that in a lot more detail, but it is just good to know. Anyway, if an electron is accelerated through a potential difference, a potential difference. What does that mean again? Well, that's a voltage, right? We know voltage is going to be involved here. So if the electron is accelerated through a potential difference in order to produce an X-ray photon with a wavelength of 76.0 pm. PM, by the way, if you're wondering what P means, you can look at your formula sheet. That means picometer. And I'll actually do that right now. Pico, I can't remember that off the top of my head. Pico is times 10 to the negative 12. So I'll even write that just underneath here, times 10 to the negative 12. That's a pretty uncommon one. We don't see that one too often. Anyway, what is the potential difference through which the electron was accelerated? Okay, this one, it might be wise just to jot down what we really know here. We know our wavelength is 76.0 times 10 to the negative 12 meters. That's one thing we know right off the bat. And since we know our wavelength, we can find our energy, because remember, energy is hc over lambda, right? So we can find the energy of this X-ray photon. That's not a big deal. What we're looking for, though, is the voltage, the potential difference through which the electron was accelerated. I guess the fact that we originally had an electron tells us that we know all the little bits about an electron as well. We know the mass of an electron, we know the charge of an electron. Those things might end up being useful here. But for now, let's just start with where we can start, okay? I'm going to find the energy of my X-ray photon. So to do this, we'll just throw the numbers we've got right into this formula. So E equals H. Just to be safe, let's use joules. 6.63 times 10 to the negative 34 times by C, that's just the speed of light, 3.00. Excuse me. Ooh, totally lost my voice there. Oh my goodness, something went down the wrong way. You guys can all laugh at that. All right, so 3.00 times 10 to the 8, and then divide that by lambda, which of course is 76.0 times 10 to the negative 12. Oh, of course, I lose my voice right in the middle of one of these. Anyway, E is equal to, I'm going to keep them like an absolute metric ton of decimals here, 2.61711 times 10 to the negative 15 joules. Cool. All right, so now we know what our energy is. That's all well and good. But we have to find this voltage from here. Let's have a look at our formula sheet. If you look at your formula sheet, look for a voltage anywhere you can find it. They're all kind of just down in the electricity and magnetism section. There is one formula that says delta V, or in other words, your change in voltage, equals delta E, which is your change in energy, over Q. Well, here's what's nice about this. This energy is the energy of our X-ray photon. Energy doesn't just come from nowhere. It has to be transferred from one form to another. This energy of this X-ray photon must have come from a change in energy of that electron being accelerated. So in other words, it went from having potential energy to kinetic energy, and that's what gave the energy to this photon. So therefore, this change in energy in our voltage formula is this energy that we found over here. So we know this piece. The other thing we know is we know Q. Q is just the charge, and since we know it was an electron that was being accelerated, we know the charge of an electron. It's 1.60 times 10 to the negative 19. So we know these two things. That means we can now find our voltage. So delta V, our voltage, our potential difference, is equal to 2.61711 times 10 to the negative 15 divided by Q, which is 1.60 times 10 to the negative 19. Throw this in your calculator. It's finally our last step here. We're going to find that our voltage is therefore 1.64 times 10 to the 4 volts. So we were able to find a voltage that an electron had to have been accelerated through in order to produce an X-ray photon with that given amount of energy. Cool. Anyway, so again, bottom line, if you're wondering how to go about these, look for what you're looking for. Find formulas in your formula sheet that go with it and try to connect the dots as much as you can. We immediately were able to find the energy of that photon. That wasn't a huge issue. Then we had to find our voltage. I just looked for a formula that had energy in it just to see if I could connect those two things together. All right, next one. I think this is the last question now. How many photons are emitted from a 1.50 MW, that's milliwatt laser, each second if the frequency of the laser light is 4.75 times 10 to the 14 hertz? Okay, so again, maybe it would be a good idea just to list out what we want and what we have. First of all, how many photons? That's what the question is looking for. We know we're looking for an N. There we go. 1.50 milliwatts. Well, think again what kind of unit watts are. Watts are a unit of power, right? So unfortunately, we know that power, as weird as this is 1.50 milliwatts, or in other words, 1.50 times 10 to the negative 3 watts. We'll come back to that in just a second. It's happening each second, so maybe we can say time is 1.00 seconds. I don't know if that'll be useful. We'll find out. The frequency, however, that sounds like it's going to be really useful. The frequency of the laser light is 4.75 times 10 to the 14, 10 to the 14 hertz. All right, first things first. We are looking for how many photons. That tells us we know we're going to have to use one of those energy formulas. So either E equals NHF, or the other one, E equals NHC over lambda. We're going to be looking for that N one way or another. Now, chances are we're going to be using this one. And the reason I say that is because we have a frequency, and that, of course, is a part of this formula. So probably we're going to have to use this one. So if we have a frequency, H is a constant, we're looking for N, but we don't know what our energy is. So logically, that tells us we're going to have to figure out energy somehow. That's where power comes into this. There's only one formula for power on your formula sheet. Power, if you find it, it's, let's see, it's in the bottom left-hand corner, literally the far bottom left-hand corner of your formula sheet. Power equals work over time. Now, let me remind you again, work is just a change in energy, right? So for all intents and purposes in this one, we can say that work is energy. So we can say power is energy over time. Well, what do you know? We know what power is. We know what time is. We can therefore find energy, no problem, right? So we can say power is 1.50 times 10 to the negative 3. And this is going to equal energy over our time. And we actually are going to use it 1 second. Times it over, not like you even have to. Your energy is 1.50 times 10 to the negative 3. And instead of that being in watts now, we would say that that's now in joules. Cool. All right, so we know our energy. We know it's in joules. Let's throw that right into this equation that I boxed up here now. Note that since this is in joules, we're going to have to make sure that we use the H value that's also in joules in order to cancel them out, right? Anyway, so E equals NHF. We know E is 1.50 times 10 to the negative 3 joules. This is going to equal N, which is what we're looking for, the number of photons, times H, which again, if we're using the one that's joules, it's 6.63 times 10 to the negative 34. And then times by F, which was known, is given to us in the question itself, 4.75. times 10 to the 14 hertz. Basically, you just got to divide each of these two pieces over to get n by itself. I will leave that to you. N to 3 sig digs is 4.76 times 10 to the 15, and the unit on that is just photons, right? It's just telling us how many photons we have, so we'll leave the answer just like that. So bottom line is, what I want you to do is get some practice by doing the photon energy worksheet, which is page 20 to 22. The questions are very much like the last couple questions I've just done here. We've made awesome time today. I'm quite proud of myself. I didn't like mess around, other than the time I totally lost my voice. Again, as always, if you need any help, please let me know. Again, just another reminder, please check your emails every single day. I do send out those email check-ins that I do require you to respond to. Just reply saying, yeah, I'm all right. And do it for any of the other classes I send it to you with. So if you're in math as well, please do it in that. Again, you know how to reach me. Best of luck.